All right, guys, so today we are going to learn our last set of derivative rules for this unit, and we are going to be learning about the derivatives of exponential and logarithmic functions. It is 4 rules that you have to learn. In some ways, it's really 2 rules in kind of 2 different parts, but 4 rules that you have to learn. And I basically have it set up. We'll just look at the rules and a few examples, and then that will be it. Looking ahead this week, so we're doing the rules today. Tomorrow we're going to revisit limits and derivatives to see how they're related. Wednesday, you know, is an asynchronous day now, and you'll be working on your briefcase binder and reviewing on your own, and I'll basically have office hours all day long. Thursday is another review day, and then your Unit 2 test is Friday. So yeah, we're quickly coming to the end of this unit. So let's go ahead and get started. Before I do the rules, I do want to review what a logarithm is. So remember, if you have log base b of a is equal to c, that is the same thing as saying b raised to the c is equal to a. And how logarithms basically work, like if I have log of base 2 of 8, and I'm trying to figure out what that is equal to, that is the same thing as saying 2 to some power is equal to 8, so I know that it would be equal to 3. There are some other things we want to remember, so like if I see just a log without a base, that's the same thing as saying log base 10. Likewise, a natural log is the same thing as saying log base e. We actually use logarithms a whole lot in calculus, especially towards like the end of this semester and a lot second semester. Particularly the natural log is used a lot, and then when it comes to exponents, the e to the x type function is used a whole lot for the stuff that we have to do. So what is the derivative of e to the x? It is, to me, the easiest derivative rule to know, because the derivative of e to the x is just e to the x. It is one of the only functions that has where the function is a derivative of itself. So basically when we interpret that, what that means is the y value on this graph is basically the same thing as the slope, which is kind of unique. Of course, things like the chain rule applies. We can do the quotient rule. We can do the product rule. But the derivative of e to the x is just e to the x. So once that will be a chain rule, just to be clear, the exponent of an exponential is considered to be the inside. So when you're taking the derivative of an e function, is basically you bring down the function and then multiply it by the derivative of the inside. So if I have this graph here, that is y is equal to e to the x squared plus 4x. 1 second. Sorry. The derivative of that is going to be e to the x, but again, the whole inside is this portion, times the derivative of the inside. So we still use the chain rule, and its derivative format is you bring it down, and then you multiply it by the derivative of the inside. Since the chain rule is pretty much going to exist for all of our functions, I am going to start writing the rule very differently. Instead of using an x in there, like saying sine of x, I'll say like sine of u. So instead of saying e to the x, I'm going to start writing all of my derivative rules from now on with the u in there. And that u is just a reminder that you have to use the chain rule. And that u also tells you where the inside of it's located at. So if I see e to the u, we can think of its derivative as e to the u times, there's the chain rule piece. And that's actually how I typed up the rule on that handout at the very top of your notes page. But whenever you see a u there, that's just your generic reminder to use the chain rule. Go ahead and try those 2 derivatives for me fairly quickly. They don't usually simplify nicely, so pretty much you can take the derivative and stop there. So again, when you're taking the derivative of e raised to anything, the derivative of it is the exact same thing you see, times the piece with the chain rule. The derivative of sine in this case is cosine. And then we have the second one, we have e raised to the x plus the square root of x. So it brings across exactly as we see it, times the derivative of the n sine. The derivative of the square root of x, we know 1/2 comes down in front, and the new exponent is negative 1/2. I don't have any examples like this in my notes, but of course from here you could do things like find a tangent line, you could find where there's a horizontal tangent, you can find the slope at a point, but right now we're just going to focus on finding the derivative. Any questions on how we can find the derivative of e to the u? All right, so that rule is important. It just works when the base is e. When the base is something else, we do have to adjust the rule slightly. So this is going to be the derivative of a to the u, where a right here is a constant. It is greater than 0, but not equal to 1. Because of course, if you have 1 raised to something, then it kind of has a different derivative. The derivative looks very similar to e to the u, so we still bring across it exactly as we see it. We still have the chain rule. The only thing added to it is we're going to multiply by the natural log of a in front. Technically, this is the same rule you have for e to the x, because the natural log of e is just 1, but whenever your base is something other than e, this is going to be the derivative rule that you use. So as an example, again, any rule that you have learned can show up. So I have y is equal to x squared times 2 to the x. So looking at this one, I don't really see a chain rule, but we are going to have to use the product rule. So taking this derivative, y prime, I have the first times the derivative of the second. The derivative of the second is going to be that new rule. So I have the natural log of 2 times 2 to the x. The derivative of x is just 1, so we didn't need to worry about the chain rule for this problem, plus the derivative of the first times the second. You can leave your derivative like that. We know with the product rule we can often simplify it. If you were simplifying this one, about the only thing you could do is take out an x and a 2 to the x, leaving everything else on the inside. Any questions on the derivative of a to the u?
Is that supposed to be ln of 2?
Yes, that should be an ln 2. Thank you.
But would it be plus 2, or do you take the 2 out of the 2x? Like the
so
2.
I took out an x and a 2 to the x. So I did leave over the natural log of 2. Oh, I messed up lots of stuff. Yeah. And that should be a 2 because I left over the 2. Wow, that was bad. Okay, so if you do simplify it, don't be like me, but simplify it correctly. And then, so those are the derivatives we have for our exponents. We also have our derivatives for our logarithms, and we do have 2 rules to look at. We have the derivative of the natural log, which occurs all the time in calculus, especially again towards December and second semester. The derivative of the natural log of x is just 1 over x. So it's kind of a unique one in that the derivative of the function is a different type of function. So like we see like the derivative of a trig function is another trig function. The derivative of an exponential is another exponential function. This one, the derivative of a log is actually a rational expression. So the derivative of the natural log of x is 1 over x. I can expand that, of course, and we know the chain rule is always going to apply. So the way I think about the derivative of the natural log of anything besides x is its derivative is 1 over the inside, and then we have the chain rule multiplying it by u prime. Oftentimes you'll see the formula just abbreviated as the inside in the denominator multiplied by the derivative of the inside in the numerator. So again, chain rule always applies. Always be aware when you have the chain rule. For my first example, I wanted to look at this one. So the derivative of the natural log of x is 1 over x. This is the natural log of x to the fifth plus tangent of x. So to find its derivative, you have 1 over the inside, and then we have our chain rule times the derivative of the inside. Which is probably easiest just to write as a single fraction. So the original inside is in the denominator times the derivative of the inside for the chain rule in the numerator. Make sure if you do try to simplify that you don't cancel across a plus or a minus sign. Questions on that rule? Try those two on your own, and simplify that first one for me completely. So finding the derivative, this is the natural log of something, so we know we have to use the chain rule. So I have 1 over the inside times the derivative of the inside. Well, that's just going to become cosine of x over the sine of x. So you can actually simplify this and write it as the cotangent of x. That's kind of a unique example because we have like the derivative of this function that's like the natural log of sine, and its derivative is just cotangent of x. The second one's kind of a trick question because if you look at it, the natural log of 2, there is no variable here. This is just a constant. And we know that the derivative of a constant is always 0. So you would say y prime is equal to 0. Of course, I guess if you did the long way, you would have still gotten 0 because you would have said 1 over the inside times the derivative of the inside. The derivative of 2 is still going to give you 0. So kind of a long way to do it. Or the short way, just kind of recognizing that as a constant. And then the last rule I wanted to show you is the derivative when you do not have a natural log. When you have a log of any other base, so base 9, base 10, base 1, base 2, anything but e. Its formula looks the same in many ways. We still have 1 over the inside. We still have the chain rule. The only thing that's added is we have 1 over the natural log of the base that you see. So in some ways it's very similar to the a to the u formula, but instead of multiplying by the natural log of the base, we are dividing by the natural log of the base. And again, this will only be used when you don't have a natural log, so a log of any other base. So to summarize, I do have an example with this, but I did want to kind of summarize and compare all of our rules first. So this is how the rules showed up on the formula sheet. So we have 2 rules for logarithms. We have the natural log, which is just 1 over the inside times the derivative of the inside for the chain rule. If you have one of a different base, you still have 1 over the inside times the derivative of the inside, but you have this added piece of 1 over the natural log of a. And then we also have the derivative of e to the u, which is just e to the u. Don't forget the chain rule. A to the u is very similar, but we have this natural log of a in front of it. And that's how I'll tend to write the derivative rules from now on with a u there, just to remind ourselves, again, that u prime is representing the chain rule. Questions on those rules in general before I do the last example? All right. So for the last example, I chose it because we've already seen some examples of problems where certain rules can be easier to use. For example, me personally, I often rewrite a problem to avoid using the quotient rule. This is one where I would probably try to rewrite it first before I found the derivative, using what we know a lot of those log properties that you've learned before. So here's the way I would not do it. This is going to be the long way to do the problem. It's not the wrong way. It would just be the long way that would kind of put you on a messy problem. If you're doing this the long way, your derivative would be, so this is a log base 3, so I have 1 over the natural log of 3 times 1 over the inside. And then we have the chain rule. Well, when I do the derivative of the inside, that's going to be the quotient rule, which is so long I don't even feel like writing it down, but you know we have low d high, less high d low, draw the line down below, the bottom square will go, and then we might have to try to simplify that. We can do this problem a lot easier if we simplify y first and then take the derivative. So I haven't found the derivative yet, but we know some properties of logarithms you could do, like the exponents can come down as coefficients. If you're multiplying, you can split it up with an addition. Or this example, if you're dividing inside, you can split it up using subtraction. And so now we will not have to use the quotient rule because now we have nothing being divided. So when I go to find the derivative of it, I have y prime. So I have 1 over the natural log of 3 times 1 over the inside times the derivative of the inside, which is cosine. And then it's minus, again, 1 over the natural log of 3, 1 over the inside times the derivative of the inside. Still, this one doesn't have too much you can simplify it, but again, we did get to avoid the quotient rule. If you were simplifying this, you could factor out 1 over the natural log of 3. Cosine over sine again is cotangent minus a rational expression. So even though this looks messy, it's not as messy as it would have been if we had to do the quotient rule, multiply by 1 over the natural log of 3, multiply this 1 over the fraction. So always be aware, if you can simplify a logarithm problem, I do strongly recommend you do, just because it does make the derivative easier, especially if you end up finding like a tangent line or a horizontal tangent or do something else with the derivative. It helps when it is simplified. Any questions on that problem? All right, so that is where I'm stopping notes today. Again, I'm going to show the calendar. Today you should be able to do homework 6. That E does stand for evens. I did realize I think I left off the last page of the chain rule, so you may not have number 76 or 84, so just don't worry about them. Homework 6, those are going to be exponential and log problems. You also do have the ability to do all of homework 7 at this point. I'll officially assign it tomorrow, but you can work on homework 7 if you want to work ahead. Again, Wednesday is all asynchronous, so definitely work on your review. Meet with me at any time to ask any questions. Thursday is review, and then your test is on Friday. What comes after this unit? Basically, unit 3 is called applications of derivatives. And unit 4 is, surprise, called more applications of derivatives. So we'll basically be applying derivatives a lot for the next 2 units. So for those of you at home, if you want to stay in the meeting, ask questions about anything, you can. Yeah, so if not, y'all enjoy the rest of your day. But if you do want to stay in the meeting, then ask questions if you have them.
Mr. Brown, I don't see homework 6 in the homework section.
Try just looking directly in OneNote if it doesn't show.
Yeah, I'm
mine
in
doesn't show
OneNote and I
either.
can't find it.
Oh, is that true for everyone?
It's not in my homework section.
Cool.
I've refreshed it multiple times.
I'm gonna just redistribute it right now then.